Hello everyone. In the last few lectures, we were discussing about recurrence relations. So recurrence relations are types of relations which can be defined with respect to itself. And we have seen how we can devise solution mechanisms for first order, second order, homogeneous, non-homogeneous, constant type variable, constant coefficient type, variable coefficient type, and many more. And we have seen many practical examples, many such examples where such kind of recurrence are automatically formulated by our recursive strategy, and we have used our formulation or our solution to those recurrences, the concepts of solutions, to solve those. However, we have seen that there are certain rules in second order or higher in case of recurrences which have a particular non-homogeneous form, which is our non-homogeneous part of the function is k into b to the power n. It may not be always the case that your function would be of the type of k into b to the power n. It could be any other functions as well. So let us first try to generalize the concept of non-homogeneous recurrences that we have solved into higher order linear non-homogeneous recurrence formulation. So the general form of higher order linear non-homogeneous recurrence is that you have of the recurrence of order k, that is it is of the Tn is dependent on other k terms, the previous k of its occurrences, and it's non-homogeneous since Fn is not equal to 0. So the order is a positive number which says that how many number of previous term a particular recurrence term is dependent upon. Here C0 is not equal to 0 and Ck is not equal to 0. So to have the order k going, and we have boundary conditions for every such k values from t0 to tk minus 1. We have a constant value here. So this is our general form of higher order recurrence and non-homogeneous one. What we have done is that we have a homogeneous solution of it, making it as equal to 0, and we have seen the higher order homogeneous recurrence solutions and its generic form as all the summations over complex reals and distinct equal roots and all. For the particular solution case, we considered that if my solution, I will try to mimic my solution as it is just like this function and try to see how this solution can aid to my recurrence. So if it exactly be with as the functions, then I have to take certain measure that I have n into that b to the power n going as per the previous lecture. So essentially we have three kind of cases can happen. First is that whenever you try to form a particular solution, your format of Fn is a constant multiple of the following table, these two types we have defined, and your is not associated with TNH. See that if you remember that how we try to define our particular solution, if it was k into b to the power n this format, then we try to see a1 or a2 into b to the power n as my answer to the particular solution. So, but if such a solution exists inside the homogeneous solution part, then we changed it using n into b to the power n or n square into b to the power n. Now we will see what is the generic rule we follow for such thing or a change. So if my Fn is of this form, that is n to the power m and r to the power n. M is a natural number, it can be 0, 1, 2 of such. R is a real number including 0. So see, this already takes care of a constant Fn, because for Fn to be constant, this form, I have to make n to be 1 or I have to make m to be 0. I have to make m to be 0 to make it as r to the power n. And in that case, if you see the previous lecture, what we have done for r to the power n, we did it with a into r to the power n. So when m is equal to 0, then this form is r to the power n. This is r to the power n and it is 0 to 0. So a 0 n to the power 0. So it becomes a0 r to the power n. That is what we have taken as particular solution when Fn is not associated with the form that your TNH provides you. Now, if Fn is associated with such a form, then we go for the second cases. But let us first finish up the other type. The other type could be it is of the form sin n theta or cos n theta r to the power n. Then also what we will take is that we take it as a1 sin n theta plus a2 cos n theta as our particular solution. So, if the format of Fn is this, we take as this. So, let's say if your r is equal to 1, what will happen? It will be n to the power m. So, this is 1, you will take a1 plus a2n plus a3n square up to a0 plus a1m plus a2m square up to am n to the power m as your solution. We will see some examples of that. Here also, if my r is equal to 1, if it is sin n theta, I will take a1 sin n theta plus a2 cos n theta as my TNP. So, these are primary two relations based on which, if it is a constant means constant into n at 1 to the power n. So, constant means m equal to 0, r equal to 1. So, then I will take some constant into 1 to the power n, that is that constant. So, we have used this in the previous part when TNH is not associated with it. We do this way. The other thing is that if Fn is a sum or a constant multiple of the above table, so it could be type 1 plus type 2. It could be n square r to the power n plus some constant into some other r1 to the power n. So, all of these cases, what we will do, we will try to see what is my TNP and try to add them, because all of them, as it was not associated with any of the homogeneous solution, it is a linear independent formulation of TNP. So, we can add them. Finally, what we can also do is when we have some association, that is your function here has a part which associates with your homogeneous solution. Then I could not directly use ar to the power n if r to the power n is in my homogeneous part. What we have done? We have done an into r to the power n. See here the formulation. Suppose you have r to the power n going inside your homogeneous part. Then what you do is that you try to, whatever for this table gives you whatever format, you try to transform it with the minimum power of s, smallest s, to multiply with n to the power of that. So, if your solution has, let's say, n into r to the power n in the homogeneous part, you will try to multiply with it n another n. So, it becomes n square into r to the power n in your particular solution. So, you need to make it linearly independent. That's why this is a rule of the table. If nothing matches with function n and the homogeneous counterpart, you can take the right column as it is, as the rule suggests. If something matches, you have to multiply with n to the power s everywhere with the smallest s possible, because that will give me the simplest TNPH. If you also increase the exponent, it is not a problem, but it is not the simplest function or the simplest ordered polynomial function that you will get from here. So, this we will follow in some of our next examples and we will see. So, one thing I left you to as an exercise, I just take type 1 matches, then we do this. What if the type 2 matches? What kind of association do we try to make? Just think it off with trying to take some examples. This is very simple if you understand the way we construct it. Let us take an example to make more clear vision to it. Let's say how many number of distinct handshakes with n persons in a party can be possible. Obviously, we know the answer, right? Because if everyone handshakes with everyone else and nobody handshakes with himself or herself, also nobody handshakes with the other person twice, then it will just be NC2 number of pairs of handshake possible, right? So, everyone handshake once with others and no one handshake with himself or herself. So, it will be NC2 number of possibilities. So, if you draw a graph of nodes with the person and the edges as the handshaking being done, you will see there will be NC2, that is n into n minus 1 by 2 number of such kind of edge. So, how can we determine this number by recurrence? what happens when an nth person comes inside a party? So let's say I have n minus 1 persons already present in the party who have already handshaked with each other. So the number of handshakes totally they have made so far is hn minus 1. Now an nth person will also make n extra handshakes than that has already been made. So therefore the recurrence is basically if the n plus 1th person comes, whatever has been already made those handshakes plus this n plus 1th person will handshake with all n other persons. So it will increment the total number by n. And if there is only one person, so no handshake with himself or herself, so it's 0. So the recurrence relation says that hn plus 1 equal to hn plus n. Obviously it is first order, first of all. It's non-homogeneous, linear, non-homogeneous, constant coefficient. Non-homogeneous because there is an n. In all the previous lectures, examples, we have seen this is of the form of a constant into some other constant to the power n. However, this is of the form of n now. So let us try to solve it using whatever we just studied as the generic formulation. Homogeneous solution hn plus 1, hn equal to hn minus 1, this will give me some constant into 1 to the power n, that is that constant itself. Now going for a solution which is of particular type, here just let us look back to this table. Our Fn is of this format because m is 1, r is 1. So it is of n to the power 1, 1 to the power n. So it gives me n. What I will choose for TNP? My r is 1, this term vanishes, and my m is also 1. So I will choose a0 n to the power 0, that is a0 plus a1 n to the power 1. So I will choose a0 plus a1 n as my format for TNP. Let us see. Yes, I have chosen this as a format for TNP. But now what will happen is that, see, if you choose this as a format for TNP, so or HNP, the particular solution, this part says a0 into 1 to the power n. Forget about this n to the power 1. This part, as per my definition, I can choose this part as a solution. Now when I choose this part as a solution, a0 into 1 to the power n matches with the homogeneous solution. So only choosing this part adding with hn homogeneous will not give me linear independent addition. So therefore I need to multiply with it n to the power s with the smallest s such that my part of the particular solution to choose become independent of my homogeneous choice. So I see that n to the power 1 is the minimum multiplication that I need to do. So it becomes a1 n square plus a0 n, which is not associated with any homogeneous solution. So with that, when it is my particular solution, what I do? I just put it here to get the values of a1 and a0 there. So let us just put it there. I do it by, so here you see when I put it here, it is n plus 1 square a1, this first part. And the second part is n plus 1 a0 for hn plus 1. And the particular solution put here is n square a1 plus na0 plus n. Now how do we solve for two constants with the single one? Because here what we will try to do, we will try to have the constant for n square to be equated on the right side constant for n square. The constants for n will be equated with the right side constants for n, and the constants without anything, or rather the single constants will be equated with single constants. But here we have a1 n square cancelled out, right? So we only have 2n a1 plus n a0 equal to n a0 plus n, which gives me a0 equal to minus half. And if we try to see the constant part, that is a1 plus a0 is equal to 0. So a1 equal to minus a0, which is half. So this way I get the particular solution constants. Now once I get the particular solution constants, I will try to formulate my final solution, which is, this is the particular solution a1 n square plus a0 n, which is half n square minus half n, plus I have the homogeneous part as a. Now I get from the initial condition h1 equal to 0. So h1 equal to 0 means n equal to 1. N equal to 1, if you put in both here, this two part cancels. So a will be equal to 0. So my answer is half n square minus half n, which is nc2, what I predicted. So see here some of the things that we are trying to formalize here. One is that you have to look for a function to seek what will be its particular solution. That is the type 1. That is the step 1 of my general formalism. So for looking at the function, looking from the previous table, I will try to figure out what is my particular function look like. If I see that this particular function has a common association with the homogeneous counterpart of the solution, then I will try to multiply with the minimum n to the power s, minimum s value such that n to the power s into this is linearly independent than this. And then only I can add them up to form the final solution. So linear independence, to make it linear independent, you need to do this jugglery. Let us try to see another examples to see this. The same examples that we have in our first lecture, when we say that we want to build how many maximum number of regions possible by straight lines in 2D plane. So the problem says that the regions formed by non-parallel, non-collinear lines. So how do we, if you remember, how do we define the recurrence relation? We say that when the n plus 1th line is introduced, it intersects with all other n lines, and while going for intersection, it increases one region, and while leaving out of the intersection from the last line, it also increases one region. So there are n lines. So while going for intersection, it increases n, and while leaving the last part, it increases 1. So total n plus 1 region, it increases with respect to whatever being present. So this will be ln plus n plus 1. Where if there are no lines, there is only one region, whole 2D plane is the region. So again, this is first order non-homogeneous, right? So again, we will invoke our previous table, but here you see my function has n and has constant. So therefore, in my table, if there are two counterparts of the function, let us go back and again see what I see. This type 2, that fn is a sum of constant multiples of the above table. So it's a constant multiple of this plus of this type. So there is type 1 plus type 1 again in this recurrence of function n. So in the particular solution, I will try to see particular solution will take two of the answers from TNP and try to add it in such a way so that it becomes independent as well. So when we do that, homogeneous solution is a simple one. It's a1 to the power n. And the other solution again we will try to seek as a1 n plus a0. Again a0 coincides with this one. So we need to go for relaxation, and then we see if I relax it here, this time a1 a0 becomes half, and then my solution becomes a plus half n square plus half n, which is as we have formulated in our earlier case, that is n into n plus 1 by 2 plus 1. So here the function n plus 1, we took help of that table type 1 property and try to figure out what will be the best counterpart for this n plus 1 thing. So you can work it by your own by dividing it into two sub functions, and then for each functions you can take it from that table and then add it. You will eventually land up to this kind of a recurrence where you will see that my a equal to 1 will give you n into n plus 1 by 2 plus 1. Let us move on. Summation of natural number square up to from 0 to n. It's a pure form of recurrence, because whatever I get till n minus 1, I will just add n plus 1 square with that answer to get the n plus 1 result. for the n plus 1 number of added summation square. So you can easily figure out that this is a classical example of recurrence, because I have 1 square plus 2 square up to n square already being computed in Sn. I will just add n plus 1 square to finally get my answer. So what is the base condition? It is S0, that is I equal to 0, it is 0 square, which is 0. Now again, this has a form called n plus 1 square. That means it has n square plus some constant into n plus some constant into n to the power 0. Now when that is the case, so for each time, again let us just go back and see it. See, when this is the case, so for each time I will try to have this addition going, right? So for n to the power n square plus n plus something, I will have a1 n square plus a2n plus a3 is in the particular solution. So by this, what do I mean is that I want to find out that this, since this is of a function of the order of n square, that is the power of 2, I will put all the terms here in the particular solution as a0 plus a1n plus a2n square. If it were at the power of 4, then I will put from a0 plus a1n plus a2n square plus a3n cube plus a4n to the power 4, everything. Now why this n? This is the smallest n to the power s, because a0 otherwise is dependent on the homogeneous solution. If any of these terms is dependent on what I computed in homogeneous, I need to multiply the whole thing with the minimum s, that is n to the power s, gives me a linearly independent particular solution than the homogeneous. Since it has a constant, I could not have constant here. So it means that this is my particular solution. And finally, when I try to go by the same methodology, that I will put this one in the original equation to solve for a0, a1 and a2. So original equation says Sn plus 1 is this part. Easily you can see I have just changed n into n plus 1. Sn is this part, and the square term n plus 1 square is this part. So hence, if you try to match the cube n cube a2 just cancels out. If you try to match the squares of n, then you will find here there is no square. Here there is a1 into n square, so a1 coefficient plus 3 into a2. So 3 into a2 plus a1 will match here with a1 plus 1, this. So therefore I get from this is the fact that a2 equal to, so a1 and a1 cancels out, so a2 equal to 1/3. Matching the square terms, so matching the n terms, which is n to the power 1 coefficients. So I get 2a1 plus 3a2 equal to, and plus a0 obviously here, equal to a0 plus 1. So 3a2, 2a1, a0 is equal to a0 plus, this would be 2, sorry, this is 2 because I am comparing the nth terms, coefficient of n. So this is a0 plus 2. So now a0 cancels out. So it becomes a1 I can get because I know the value of a2. So a1 becomes 1/2. Now comparing the constant coefficients, we will get here a0. This is a1 here and a2 here will sum to 1. So then I will just get a0 equal to 1/6. So therefore my particular solution has a more concrete version. So it is 1/6 of n plus half n square plus 1/3 n cube plus the a is the final solution, a plus all this. So now if your S0 is equal to 0, so you put there 0. So here everything is 0 except a. So a is 0, I am getting it. So it is 1/6 n plus half n square plus 1/3 n cube. If you simplify it by a fractional kind of an answer, you will see n into n plus 1 into 2n plus 1 by 6. Isn't it the right guess? Because 1 square plus 2 square plus 3 square up to n square is this closed formula as we know from school. Now your job is to find out the generic form of this kind of formulas, which is this. So what I do is here, what I kept it for you, that linear sum will come as, you know that n into n plus 1 by 2 will come. Here the cubic sum, do you have a formula? Then try to match it. Quadratic sum, do you have a formula? Then try to match it in general sum. Okay, so this you do it by our non-homogeneous recurrence solving process and get the same sum. If you have a formula, just match it with it. So I left it as an exercise for you. So this completes our discussion, and we have a variety of techniques to cater our recurrence relations and to make a solution for it. One of the techniques is going by a guess and proving through mathematical induction. The other could be just expanding it. The more formal techniques would be that to use the homogeneous and non-homogeneous part, if it is a non-homogeneous type of recurrence relation, to use the non-homogeneous and homogeneous counterparts, try to eliminate the constant of the particular solution, try to see the constant of the homogeneous part by using the base condition, and try to finally come up with a solution. That is what we have done. If there are conflict and making it linearly independent or linearly dependent, then you need to make it n to the power s multiplied with a particular part to have linear independence going. So this is what we have studied so far. But there are some other recurrences which we call as a special type of recurrence. We will come in a minute. But before that, let us try to concentrate on, there is a concept of generating functions that we have already studied. So generating functions are basically techniques which tries to bound you or give you a closed form of a sequence or a repeating operations. As you have seen, you are trying to bound a closed form for a sequences. And repetitions, recurrence relations are nothing but such kind of a repeated sequences. Let us try to see how generating functions can be invoked to solve such recurrences, and it's a very easy tool for us to solve the recurrences. Apart from all the jugglery we have learned, if we can use generating functions, some of our jobs is much more simplified. So one of the examples is that, how do we select R objects from n distinct objects with repetition? Let's say n distinct object, I want to choose R. So I have A n R, but it's with repetition, remember. If you know the formula, just hold on with you. Let me see that whether I can reach there. What will be the recurrence? Here we go. Either we take an object, or we at least once, or we never take that object. So if we never take that object, so the R objects I have to take from n objects. So one particular object in n I never take into my solution. Then for the remaining n minus 1 object, I need to choose R of them. And what is the other part? That I take one particular object always or at least once in my combinations. So in that case, the remaining R minus 1 objects, I need to choose again from this n, because I am allowing repetition. If I haven't allowed repetition, then I have to choose it from n minus 1. But I have allowed repetition, so again those n minus 1 I can choose. So at least one that object, maybe more than once I may choose, but at least once it has been taken. So with this concepts, the recurrence becomes A and R, choosing R objects from n with repetition, is choosing, leaving out one object for sure from n and choosing R objects from, excluding that from n minus 1 objects, and at least one time choosing that object, and for the remaining objects again I choose it from n. So this is my recurrence. Remember earlier we had recurrence with one particular term index going, here it's a 2 index going. Where if you have to choose no object from n, this is 0 way you can do it. So there is no way that, there is nothing to choose, that's why 0 is the answer. If there are no objects but I tell you to choose something of them, you cannot do it, so it's a 0. So these two are my base conditions. Now let us see how can we solve this recurrence. We have the base conditions, we have the recurrent relation. It's a two-dimensional recurrence to that sense. So let us try to have, so see what we want, I want A and R. So let us try to have a sequence with respect to n and with respect to R, such that if I can solve this generating function, then my x to the power rth coefficient would be my answer. If I could solve this generating function, then my x to the power rth coefficient would be my answer. Now how can we solve this generating? How can we express this expression using the generating function. So what I will do is that I will try to multiply everything with x to the power r in both way and then take a sum from r equal to 0 to infinity, which gives me this. So I just multiply everything with x to the power r and take a sum from r equal to 1 to infinity. What does it say? That this expression is the generating function for this. So this is the generating function for f and x minus when r is 0. So minus a n0 x to the power 0 means, which is f. So this is nothing but this one, right? F n x minus a n0 x to the power 0 is 1. So this is nothing but f n x, where you included from r0 to infinity. So just I have to minus it. What is this one? This one, if you take out one x from it, it will be r minus 1. So r minus 1 goes from 0 to infinity. This is same as f n minus 1x, because this part is n minus 1. What is this one? This one again, if you see that if I take r, so just a mistake. So this one I do not have to take an x. So it is just in the form of x to the power r. Here is r. This is n minus 1. So again, going by the previous analogy, I will get it is f n minus 1x minus a n minus 1 0, because f n minus 1x starts from r equal to 0. So this part translates here. For this case, since this is r minus 1 and my generating expression says always x to the power will be equal to this one. So I need to take out an x outside the summation, because summation doesn't depend on an x. So take out an x to get it as x to the power r minus 1. Take out an x. Now I see that r minus 1 is equal to 0. So it goes from 0 to infinity for some n. Let's say this is m x to the power m. So this is nothing but f n x. So my term becomes f n x minus 1. So this is 1, and f n x minus 1 minus 1. So just a clarification, this is wrong. This should be 1, because if I give you n objects and you need to choose nothing of them, there is one way that I do not take anything. So that is one way. Whereas if there are 0 objects and you have to choose something of them, there is no way to do that. So this should be 1. This is a mistake. So that's why this is 1. This is 1. And solving this, I get f n x is equal to f n minus x by 1 minus x, which is equal to f n minus 2x by 1 minus x square. F n minus 3x by 1 minus x cube goes down to f0x by 1 minus x to the power n. What is f0x? f0x is equal to 1. Okay, because I have said that both of them this is a mistake in both of these sides. This should be 1, because if there are n objects, I do not choose anyone. This is in one way that I will not choose anything. If there are no objects but I need to choose, there is no way. That is one way that I do not choose. I cannot choose anything. So f0x is basically a0r x to the power r, this summation. Now, if a is equal to 0, then there is only one choice possible for every option. So this goes down, this generating function goes down to 1 by x, 1 minus x whole to the power n, which means that it is 1 minus x whole to the power minus n. So now see that this function, if I try to compute the coefficient of x to the power r here, then I will get my answer, because x to the power r coefficient is a n minus r. So now the question is, what is the coefficient of a n r? It is this. So this means that it is n plus r minus 1 CR. So now, do you remember the formula that n distinct objects you have to choose r from them? With repetition will give you this as an answer. So let me repeat whatever I have done. So I have tried to formulate a recurrence, which is not a single term recurrence, single parameter recurrence of a term. It's a 2 parameter involved. Now I have seen that no object choosing is not, there is only one possibility, that if you do not choose any objects from n, and if we do not give you any objects, there is it is invalid that whatever number you choose. Now I have generated a function where my coefficient of x to the power r will be my answer, and I tried to formulate this recurrence in those terms. And when I try to formulate that, I get that an expression which is fnx equal to fn minus 1x by 1 minus x. So if I just go by the geometric progression in this way, if I try to expand it, it will be f0x 1 minus x to the power n. Now what is f0x? f0x is nothing but your n is 0. So this is 1. I mean, if this is 0, then no matter whatever you take, you will just have nothing to take, that is one option. So therefore, the coefficient of ANR will be the coefficient of x to the power r in this expression. And finally, we found out that the coefficient is minus NCR into minus 1 to the power r, which is this. Let us change it a bit to clarify more that whether choosing n objects, r objects from n distinct objects without repetition. Since we are using without repetition, you know the answer, right? NCR. Let us see. So without repetition means that when I say a particular object is never selected, it means that I need to choose r objects from n minus 1 remaining objects. One objects I will never select. And when I say each object is once selected without repetition, that means I select that. The remaining r minus 1 I will choose from the remaining n minus 1. So any other choice will not select it anymore. Repetition is not allowed, that's why. Same way, ANR equal to AN minus 1 R and AN minus 1 R minus 1. And again here there is a mistake, it will be 1. So there is only one way. If you do not give me any object, I will not choose. This is the only way. So again, go by generating function and see what is the formula and the coefficient of x to the power r. So we have done this way. This way will come, only this factor changes a little, which becomes earlier it becomes x into fnx. This time it becomes x into fn minus 1x. So this goes as fnx equal to 1 plus x into fn minus 1x, which means this is 1 plus x whole to the power n into f0x, which is 1. So it goes as a 1 plus x whole to the power n, and as you can see, the coefficient of ANR is nothing but NCR. That is choosing R objects from n total n total objects without any repetition is just NCR. So we have seen this, right? So this is how you see that there are recurrences which is very complicated in nature, where two parameters are getting varied. So by the virtue of generating function, we can easily formulate it in terms of a polynomial whose coefficient is my generating sequence, and finally can get out my answer. So to experiment more with generating functions and recurrences, all our earlier examples that you have given, you can use the invoke similar kind of generating functions and try to find out the corresponding coefficients which will give you the answer, and see that those answers that we derived using our formula comes. So that is what the generosity of generating function I would say, and we can take much help from it. As I have pointed that this is not all, and we also have some other functions to talk. So our third kind of thing is that it may be the case we have seen in case of forming number of regions by bent lines, that there are a recurrence which can invoke other recurrence. So what if there are two recurrences which invokes one another in the process? Let us take an example which we call as system of recurrence relations, and how do we solve it? So upon interaction with a nucleus of fissionable material, the following activities happen. A high energy neutron fissions with nucleus and releases two high energy and one low energy neutrons. A low energy neutron, when get a fission with the nucleus, releases one high energy and one low energy neutron. So the question is, after n such interactions or fissions, how many high energy neutron and low energy neutron you will get in the system, provided you start with only one high energy neutron. So therefore, my recurrence would be An is the number of high energy neutrons, Bn is the number of low energy neutrons. And we assume at beginning that A0, that is the high energy neutron, is 1 and there is no low energy neutron. So the condition 1 says that every high energy neutron releases 2 high energy and 1 low energy neutrons. So An plus 1, the number of high energy neutrons will be 2An, because this one releases 2 high energy neutrons, plus Bn, because 1 low energy neutron releases 1 high energy. So Bn number of low energy neutron releases Bn number of high energy neutrons. Similarly, the number of low energy neutrons at n plus 1th step will be every high energy neutron releases 1 low energy and every low energy neutron releases 1 low energy. So it will be An plus Bn. See here the types of recurrence. It's a system or a series of recurrence relations where each recurrence relations is not only dependent on the previous of its term but also dependent on a term which is a previous value of the other recurrence. We have to simultaneously solve this, right? Let us see how we do that. We take help of the generating function. So we need to generate what is An and Bn. So we will generate a sequence where my x to the power n term will give me the answer for both of them. Let fx be a generating sequence for An and gx be a generating sequence for Bn. So this we usually do looks horrible, but this is a simple jugglery where I have just multiplied everything with x to the power n plus 1. An plus 1 x to the power n plus 1 equal to 2an x to the power n plus 1 plus bn x to the power n plus 1. And then take a sum over n equal to 0 to infinity every side. This gives me, if I take out this x, this will be this part. If I take out the x from here, because it's to the power n plus 1 both position. So what does this gives me? This is nothing but your n is going from 0 to infinity. So n plus 1 is going from 1 to infinity. So it is nothing but fx minus a0, because one term we are missing here. Here it is just fx, so 2x into fx. Here it is just gx, so x into gx. What does this mean? This means again it is gx minus b0 equal to x into fx plus x into gx. Now we have two such equations, fx and gx are the two unknown quantities. Solve it and you will get this. If you solve it with a0 equal to 1 and b0 equal to 0, we will get fx equal to 1 minus x by x square minus 3x plus 1 and gx equal to x by x square minus 3x plus 1. The rest I am not telling it to you because it's a simple jugglery to form this kind of some alpha minus x and beta minus x, some gamma minus x and delta minus x. Because unless we form it in this way, I need that something minus x to the power minus n to get my x to the power n coefficient. Remember, my job is to get the coefficient of x to the power n. From here it is not obvious. As you have seen in generating function class, that we make certain jugglery to make it as 1 minus x to the power minus n or 1 minus x, 1 plus x to the power n, this format. So once we get that, we find this as an answer. So I leave it to you to experiment over this, because from here to here you will just have to take a factor of it and try to build this one. And once you build this one, it is simply that you can easily see this is this minus this to the power minus n will be there, where because it is x to the power n is the nth term that we are trying to consider. So this is to the power minus 1. The nth term will be this one and the nth term for other one will be this one. So this results. You can verify it just using the concept of generating function calculations. So with all this, we come to solve some special recurrences which does not obey the formula of this homogeneous, linear and all this. It's a non-linear kind of recurrences. So let us see some of the recurrent problems which you have some of which you have seen earlier in your counting classes and already solved it in a different manner. We will use recurrence to solve the same and elegantly. Number of ways to parenthesize an n-length expressions. We will use one type of parenthesis. How many ways we can do it? All this question will result to an unique answer, but first let me pose the questions. Number of different ordered, unleveled, rooted n-node binary tree. So how many ways you can formulate a binary tree which is rooted, unleveled, ordered, and how many ways you can do it? Form it. Number of non-overlapping handshakes among n persons seated in a round table. So no handshake should cross one another. This is same as telling us number of non-intersecting chords of a circle with endpoints located in its perimeter. Number of paths in an A cross B grid from the bottom left corner to the top right corner not crossing the diagonal. Now you can understand, right? You have done it. Number of triangulations possible in an n-sided regular polygon. Number of stacky sequences, which means that I will try to push 1 to n in an order and pop and print anytime unless the stack is empty. What is the realizable sequence that I will get as my output of the print? So you can see that obviously 1, 2, if you try to push 1, 2, 3, 4 in order and try to pop in between, there are some sequence you cannot get. So those sequences are not stacky sequence. How many of the stacky sequence are possible? So all of them, if you have get some answers to it, all the answers are equivalent, I would say. And it's nothing but the magic is the Catalan number. So let us see that how many ways you can parenthesize. Take this example. The other examples will follow the same approach with this expression of recurrence. So n plus 1 length sequence to parenthesize. I will not parenthesize anyone in the beginning. I will all the n together in a parenthesis. How many ways I can do? One symbol or one in the string as opening and closing bracket around it only, and the rest n minus 1 as the total parenthesis that I get from. In this way, I could construct these many number of parenthesis options. So all of them added to get my number of parentheses for n plus 1. So this is a non-linear, but it's a weird kind of a recurrence which we never thought of in our previous encounter of generic recurrences. Obviously, if we have nothing, there is one way to parenthesize, that is you just put an empty bracket, nothing else. This is the base condition. Now we apply generating function to get the coefficient of x to the power n as my answer. But here the generating function is of a different nature. So let us anyway try to apply it. What does it mean? It means an plus 1 x to the power n plus 1 equal to, this is just the summation I have written x to into x to the power n. So if you have seen this term, how this term is getting generated, if you try to figure out, you will see it is fx square. If you take out 1x outside, this term into x to the power n gets generated by fx into fx, this generating function. What is fx into fx? Fx into fx, the nth term will be an into a0 plus an minus 1 into a1 plus an minus 2 into a2 and so on. Fx square, the x to the power n coefficient, is the generating function here, is just this summation of the terms. So we can write it this way. Now it's a quadratic kind of fx square, where if your fx equal to 1 plus minus root 1 minus 4x by 2x. If you try to simplify it, what you need? I need in this generating function, what is the coefficient of x to the power n? That is my answer. So to get the coefficient of x to the power n, I need the coefficient of 1 minus 4x to the power minus half. There I need the coefficient of x to the power n plus 1, because x to the power n plus 1 term will get cancelled with 1x, give me x to the power n. So in the 1 minus 4x root, there I need what is this sequence of, and what is the x to the power n plus 1th coefficient of it. So this sequence, if I use the Maclaurin series and just expand it, this sequence will be half c choose n plus 1 minus 4 to the power n plus 1 is the n plus 1th term. Expand it, solve it, nothing, you will get this sort of a form. Now try to put it here to get the final coefficient. What will be the final coefficient here? This, I am just taking the negative one, because if you take the positive one, this term will become negative, and that will not solve our purpose, because the number of ways to parenthesis n plus 1 string cannot be negative. So only the negative choice will help us. Now when I put it here, so the coefficient of half into this one is my answer. Simple algebraic expansion of this n to n plus 1 choose n plus 1, and then manipulation will show you it's a Catalan number which we already know of, 1 by n plus 1 to NCM. All of these recurrences, if you formulate, will be either in this form or some variant of this, but however you solve, you will get eventually, if you use generating function, it will be much easier, and eventually you will get an answer which is of the Catalan form in nature. So these are some kind of special recurrence which is non-linear obviously, but it's a kind of different non-linearity we expected. We expected non-linear to be a1 n square log a n plus 1. These forms we have seen, but this kind of form we have never seen, and this is an example for that. So in this lecture, we have understood that how we will deal with non-homogeneous part of the function and how we will have type 1 and type 2 kind of properties to extend to the linear independence nature going in the solution. We have also seen how we can invoke generating functions and can solve the recurrence relations which is not only dependent on the nth term but also is a 2-parameter recurrences. We can also use that generating functions to evaluate the single parameter recurrence as well, and we have also seen that how such kind of complicated or special kind of recurrences we can build, and see that if you can formulate it in terms of generating function, it's only the x to the power nth term coefficient you are trying to seek, because you are only going to answer an, your generating function is going to give you that if you take the coefficient of x to the power n in the final form of fx. To get the final form, we use the arithmetic juggleries and finally the series and expansions and come up with the nth term coefficient, and that is our answer. So all this completes our basic recurrence relation tools or technologies or methodologies that we could use to formulate and solve recurrences. In algorithms, apart from that, there are some other kind of recurrences we will encounter, which is basically how we think of solving a problem by dividing and conquering it. We will try to see there is a lot more these types of recurrences which is used in algorithmic sense or algorithm analysis or problem solving, and there is a whole lot of technologies or methodologies that we can use to solve such kind of a recurrence. We will see that in our future lectures. Thank you.